So the question from the audience is, how come we execute main, but for what reason all of these outputs become available? The reason is that when we create a function do stuff, and when we start making calls to that function, main stops executing. Do stuff executes and does whatever it's programmed to do, and it returns back, and then the next one, the next one, the next one. So we get this statement is part of do stuff, and these are function calls. Okay, so the function do stuff gets invoked multiple times, 5 times. Right? So this code executes 5 times. Every time you say do stuff, it goes in and executes this, okay? Executes those 3 lines.
I was asking for purpose of scope. If you're invoking scope on the bottom, how can you pull it into it?
Because, yes, so how come we don't get main and we get do stuff that gets printed here? The reason is that every time we make a function call, we enter the scope of this function, and therefore this prints do stuff and not main. Okay? Because this thing is within do stuff. And so that's why this gets printed here. However, if I wanted to print the same thing here, at the end I can say the name of this function is, okay, and just say what the name of my function is, right? Just print, get rid of this, and print new line at the end. So that prints main, okay? Because this function is right here in the scope of main, and this function name is right here inside the do stuff. I am just showing this to you because sometimes, I forget I have to stay close to my laptop and not walk away, otherwise the recording is disrupted. So it's a useful debugging facility to be able to display the name of your function. I just thought that would be something I can show you today. But let's move on. We still have more things to talk about. Again, this is all recorded. You will be able to replay it. Hopefully, you can get some ideas from what I'm trying to do and what happens. But I'm not trying to focus a lot on any specific programming language, just trying to talk about variables and their existence in memory today, right? So this happens very informally right now. Okay, just know that all local variables, like pi, are stored in the stack. Stack is the memory, which we're going to discuss in much greater detail when we talk about function calls and method calls in Java. In both CIS 157 and CIS 123, we will return to discuss the local variables in greater detail when we talk about function call mechanism, function return mechanism, and stack manipulation in general that takes place when we make calls of any kind. All right, but anyway, today's knowledge is local variables live in the stack. It's good knowledge. Everything I'm telling you is good knowledge. So heap memory is something we will be able to discuss again in detail in a few weeks. I would like to, well, perhaps let's just try this very quickly so I can walk you through what this little example does, and we can move on to other things. But hopefully it's not going to take me too long, so I'm just going to erase what I have right now and replace it with this sample. Let's walk through this. You already know that cout is the console output, and when you give it a literal string like this, it's just simply going to print this on the screen. In my case, this is going to create a prompt to a user who is using the program. Then I'm declaring local variable count of type integer. So it's just basically a variable that can hold numbers. Okay, this local variable is not initialized with any kind of value. I typically, when I really don't have a value to initialize my variables with, I usually give them 0, something like that. But here I didn't do it from the beginning because right on the next line I use SIN, which stands for character input. SIN is character input. It's the opposite of cout. SIN gives you an ability to say, hey, I would like to get input from the keyboard. And here I say, how many numbers would you like to allocate? And simply wait to whatever they type. So once they type something, I'm actually going to create a memory block and say, I want this many integers in memory. And I will say, your block of memory begins at address such and such. Okay, kind of overwhelming, but this is an example here of using heap memory. So again, I don't want to go into any details. I'm just going to run this and I'm going to say, how many numbers would you like to allocate? Okay, maybe I want 10. Okay, so it will dynamically ask the operating system to say, give me memory for 10 integers. Each integer, by the way, takes perhaps 4 bytes in memory on the system. So 10, hit enter, and it says down there, your block of memory begins at address 0x1141B70. This is, by the way, a hexadecimal number. Hexadecimal numbers are uniformly accepted to represent memory locations. More about this later on. But you can see that this address right there that was just printed, this kind of garbage, right? It's a crazy number, whatever. It's a number. It represents that memory address, and that memory address is actually in the heap memory, which is designed to allocate memory dynamically for us. So once again, the heap memory, if I go back to the picture here, the heap memory is right here, and this is the example of using it. As you can see, there were lots of things happening, and my example here demonstrated that I wanted to create this many integers, and I had to use the new, which actually is using the heap memory and allocates a block of memory with that many integers. This is not very useful because I'm not really doing anything with those 10 integers that I was able to allocate, but I do demonstrate to you that the numbers are created dynamically at runtime, and you can see that their address is such and such. They really do physically present themselves, which is fine. Okay, so those things are important because it's just good knowledge that stuff is really happening this way. Now, I would like to tell you one more thing, which is this bullet here, that when you look at this picture, we say heap, which is heap memory segment, but in C++ terminology, we say that the dynamic memory, which allows us to create things at runtime dynamically, is not called heap, it's called free store, okay? It's just a one technical detail, because in C++, dynamic memory manager is different compared to C, okay? But you should know that heap and free store are almost the same thing. C programs exclusively use heap for decades, and C++ programmers prefer to refer to dynamically allocated memory as free store. Okay, more about this in the future. All right. So moving on, what is local variable? Apparently, we were ahead of time when we said few things about local variables. Local variables are those variables that are declared in a scope of a function, such as this function f. Okay, so for instance, I can take this Control C and paste it somewhere here and say, oh, my program besides main also has function name f. By the way, it's easy to use single character names in your program, but in fact they're kind of horrible because it's very difficult to search for single character names. So this is not a good name. So let's say foo is a better name, right? Even 3 characters like that is better than F, and it's just something I want you to realize early on. So it creates a local variable. How do I know this? Because look, there's function, it's called foo. It's creating a local variable, and that local variable, of course, is enclosed in these braces. Therefore, it's a local variable that belongs to function foo. Now, notice that foo does not have a return statement, right? Does not have this return statement. It's because it says, I am void. A void is right there, is specified right in the position where return value type of functions is specified, and void says do not expect anything from a void function. You cannot expect this function to compute something and give you the result. Okay, just cannot do that. So that's why we call it void.